Hello students, from this video I am going to start your unit number 3 of paper 2, that is Laplace transform. So let me hide myself so that you can see whole writing screen. Okay, so before starting anything, I suggest you to have your notebook and pen along with you so that you can follow my steps in your notebooks. Okay, so what Laplace transform is? A Laplace transform is a kind of operator which operates on some function to give another function. Okay, so let us see the definition first of this Laplace transform. Definition, sorry, definition. Let f of t be a real valued function defined for t greater than 0, then a Laplace transform of f of t is defined and denoted by L of f of t equals integration from 0 to infinity e to the power minus st into f of t dt, and the transformed value of the function f of t is denoted by capital F of s, or it is sometimes written as f of s. Okay, so read the definition again. Let f of t be any real valued function defined for t greater than 0, then the Laplace transform of function f of t is defined as this: L of f of t equals integration from 0 to infinity e to the power minus st into f of t dt. Okay, let's see some examples. Example means we will see the Laplace transform for some elementary functions. So Laplace transform of some elementary functions. So let us take first function as t to the power n. Number 1, f of t equals to t to the power n, where n is non-negative integer. Okay, so in order to find the Laplace transform of this function f of t, you just follow the definition of Laplace transform. See what Laplace transform is. I mean what Laplace transform of function f of t is Laplace transform of f of t equals to integrate this integration. Okay? If you have to find, if you want to find Laplace transform of this function, that is t to the power n, you just replace f of t from the definition of Laplace transform. So let us do that. We start from given. Let f of t equals t to the power n, where n is non-negative integer. Okay, from the definition of Laplace transform, we have, what is the definition of Laplace transform? It is L of f of t equals to integration from 0 to infinity e to the power minus st f of t dt. Okay, so put f of t equals to t to the power n in above equation. What will we get? We get Laplace transform of t to the power n equals to integration 0 to infinity e to the power minus st t to the power n dt. So in order to find Laplace transform of t to the power n, you have to solve this integration. As you can see, this integration, under this integral sign, there is a product of two functions. One is exponential function and other is algebraic function, and such integrals can be solved by using integration by parts. Hope you know what integration by parts is. For you, I will write that here. In integration by parts. What is that? Integration of first into second function is equals to first into integration of second function minus integration of derivative of first function into integration of second function. Okay, and how will you determine which one is first function and which one is second function? From LIT rule. LIAT rule. L stands for logarithmic function, I stands for inverse function, A stands for algebraic function, T stands for trigonometric function, and E stands for exponential function. As you can see in this equation, there are two functions. One is exponential function and other is algebraic function. So this must be the first function we are going to treat, and this as a second function. Okay, so let us integrate this. So Laplace transform of f of t equals to first into integration of second. So our first function is t to the power n into integration of second function, that is e to the power minus st dt, minus integration of derivative of first function. First function is a t to the power n, and derivative of t to the power n will is n into t to the power n minus 1 into integration of second function. What will be the integration of e to the power minus st? It will be e to the power minus st upon coefficient of t, that is minus s dt. Okay, so we go to the next step. Here also integration of e to the power minus st will be e to the power minus st upon minus s into t to the power n with the limits 0 to infinity. Here n and minus s in the numerator and denominator respectively are constant of integration. So you can bring them out of integral sign. We get this minus and this minus plus n upon s integration 0 to infinity t to the power n minus 1 e to the power minus st dt. So we move further in the next step. So Laplace transform of t to the power n equals to, you can take minus 1 by s outside and apply the limits of, that is upper limit and lower limit to this part. So at upper limit, that is at infinity, what power of e becomes infinity. So and e to the power minus infinity tends to 0 obviously. I hope you know this. So as e to the power minus infinity tends to 0, 0 into anything will be 0. So first part of this will be 0. Let me write this step in detail, but in the later examples I will do that directly. Okay, this is infinity to the power n e to the power minus infinity minus, what is the lower limit? 0. When you put here t is equals to 0, 0 power n 0. Okay, so this is 0 into e to the power 0, bracket close. And what about this integration? Here again we should apply integration by parts. So what will be this? First into integration of second. Here this is second function, this is first function. So first function, that is t to the power n minus 1. Integration of second function will be e to the power minus st upon minus s with the limits 0 to infinity minus integration of derivative of first function. What will be the derivative of first function? It will be n minus 1 t to the power n minus 2 into integration of second will be e to the power minus st upon minus s dt. Okay, so we move further. So this is Laplace transform of t power n equals, so e to the power minus infinity becomes 0, 0 into anything 0, minus 0 into this is 0. Okay, so this first part of this whole expression becomes 0, and what is there? N upon s. Solve this. Here again at upper limit this exponential function will tends to 0. So first term after applying the limits will be 0, and at lower limit, that is 0, this t to the power n minus 1 will become 0. So 0 minus 0 again 0. So this part becomes 0. So we are not going to write that part. And what remains here? See, n minus 1 and s are constant of integration. So both can be taken out of integration, and this minus becomes plus. So this is into n minus 1 upon s, and what the remaining things? Integration 0 to infinity t to the power n minus 2 e to the power minus st dt. ठीक है? So what are you observing here? In the first attempt of integration by parts, what we are getting? This n by s out of the integration. Okay, and after applying second integration by parts, we are getting n minus 1 by s out of the integration. So continuing this process, what will we get? Laplace transform of t power n equals n into n minus 1, then we get n minus 2, so on 3 into 2 into 1 upon s to the power n. Okay, and what inside the integration remains? Integration 0 to infinity e to the power minus st dt. Okay, so you should write continuing this process. Okay, so and what will be the final integration? That is integration of this Laplace transform of t power n equals, see, this is the product of n into n minus 1, n minus 2, so on 3 to 1. This is nothing but your n factorial upon s to the power n into integration of this. You can evaluate this easily. What is the integration of e to the power minus st? This will be e to the power minus st upon minus s with the limits 0 to infinity. What it equals? It will be n factorial upon s to the power n e to the power minus st at upper limit, that is infinity. This will be e to the power minus infinity minus e to the power minus st at lower limit, that is 0. It will be e to the power 0 upon s, particularly minus s. Okay, so what will be the final answer? Laplace transform of t to the power n equals to n factorial. See, e to the power minus infinity becomes 0, minus e to the power 0 becomes 1. So 0 minus 1, minus 1, this minus 1 upon minus s will be 1 upon s, and 1 upon s into 1 upon s to the power n, this will be s to the power n plus 1 whenever n is non-negative integer. Hope all this whole calculations are clear to you. So what did we get? The Laplace transform of which function? T to the power n. Okay, so in the end we will write Laplace transform of t to the power n is n factorial upon s to the power n. Okay. This. You take a note of this equation. In the later example, we will require this equation, or now you can say this as a formula. Okay. So let us see some particular example of this. As it is written here, n is a non-negative integer. So put any non-negative value of n. Example, Laplace transform of e to the power 0. This will be 0 factorial upon s to the power 0 plus 1. That is 1 upon s. Okay. What will be the Laplace transform of t power 1? This will be 1 factorial upon s to the power 1 plus 1, which equals to 1 upon s square. Okay. In this way, you can find the Laplace transform of t to the power non-negative integers. So let us write the higher power of t, that say 5. What will be the Laplace transform of this function? It will be 5 factorial upon s to the power 5 plus 1. That is, what is 5 factorial? It is 5 into 4 into 3 into 2 into 1. That is 120 upon s to the power 6. Hope you are getting this. Okay. So here in this above example, the Laplace transform of f of t, Laplace transform of t to the power n is found, where or when n is non-negative integer. What if n is negative integer or particularly negative number? So to find the Laplace transform of such t power n when n is not a non-negative integer, we will require gamma function. All about gamma function you have studied in the previous semester. So here we are just recalling the definition of gamma function and some formulas we have derived in the previous semesters. Okay. So recall gamma function. Okay. What is the definition for gamma function? It is gamma n equals integration from 0 to infinity t power n minus 1 e to the power minus t dt, where n is positive. This function is known as the gamma function. Okay. So one more I would like to write, which will be helpful in the later examples. What is gamma n plus 1? All this you already did in the previous semester. What is gamma n plus 1? This is n gamma n or n factorial when n is positive. And what if n is negative? Let me write that also. Remember, this is when n is a positive. When n is negative, when n is negative and not equals to any negative integer, that is -1, -2, -3 and so on, then we will use gamma n equals to gamma n plus 1 upon n. Okay, also gamma, what is the value for gamma 1? It is 1. Okay, and what is the value for gamma 1 upon 2? It is under root of pi. All these formulas will be required to find the gamma function of t to the power n, sorry, the Laplace transform of t to the power n when n is not non-negative integer. Okay, so let us find that. Okay, now Laplace transform of t power n equals to question mark if n is negative and not equals to -1, -2, so on. Okay, so again we will recall the definition of Laplace transform here. So by definition, Laplace transform of t power n is integration from 0 to infinity e to the power minus st t power n dt. Okay, here what we will do, we use the substitution method. And what will we substitute? Put, say, we have already used t as a variable, so let us use u. Put u equals to st, then what will be du? It will be s dt. Okay, and what about the limits? The limits are unchanged. How? These are the limits of t when t is equals to 0. Put here, when t is equals to 0, u equals to 0, and when t is equals to infinity, u is equals to infinity. So limits are unchanged. Limits are unchanged. Okay, so do the substitution. Laplace transform of t power n equals to integration 0 to infinity e to the power minus u, and what will be t to the power n? It will be u to the power n upon s to the power n, and dt equals to du by s. What will be the next step? Laplace transform of t power n equals to 1 upon s to the power n plus 1 integration 0 to infinity u to the power n into e to the power minus u du. Now see the definition of gamma function. What was that? This gamma n equals to integration 0 to infinity to the power n minus 1 e to the power minus t dt. And what we have in our example, integration from 0 to infinity u to the power n e to the power minus u. What adjustment we do here to get the gamma function? See, 1 upon s power n plus 1 integration 0 to infinity u to the power n plus 1 minus 1. You can always adjust there into e to the power minus u. Then what it becomes from definition of gamma function? It will be s to the power 1 upon s to the power n plus 1. This will be gamma function of n plus 1. Okay, so what did we get? The Laplace transform of t power n equals to gamma n plus 1 upon s to the power n plus 1. Okay, with, since n is chosen to be negative here, so how will we find gamma n plus 1? By formula gamma n plus 1 upon n. Okay, where n is negative and n not equals to minus 1 minus 2 so on. Hope this is clear to you. So take a note of these transforms. So let us see one more example. Number 2, f of t equals to e to the power at. Now we will find the Laplace transform of this exponential function. So let us start. We start from given f of t equals to e to the power at. By definition of Laplace transform, we have Laplace transform of f of t equals to integration 0 to infinity e to the power minus st f of t dt. Okay, what you will do? Replace f of t by e to the power at. Put f of t equals to e to the power at in above equation. What will we get? Let us see that on the next page. We will get Laplace transform of e to the power at equals to integration from 0 to infinity e to the power minus st e to the power at dt, which equals to integration 0 to infinity e to the power, can write this as minus s minus a t dt. Okay, and do the integration. What is the integration of this? This is e to the power minus s minus a t upon coefficient of t, that is minus s minus a limits 0 to infinity, which then equals to minus 1 upon s minus a, this function at upper limit minus this function at the lower limit. So what this function becomes at upper limit? E to the power minus infinity minus this function at lower limit, that is e to the power 0. As we did earlier, what is e to the power minus infinity? This tends to 0 and this is 1. So 0 minus 1 minus 1, and minus 1 into this minus 1 will be 1. So we get 1 upon s minus a. Okay. So what is the Laplace transform of e to the power at? Therefore, Laplace transform of e to the power at equals to 1 upon s minus a. So this part I am leaving on you. Check this whole solution. Why I have written here s is greater than a. Okay. Remember this also. So example, take example of this also. Example, what will be the Laplace transform e to the power minus 5t? Okay, because a can be any constant. If you want, you can write a is any constant. So by this above formula, what will be the Laplace transform of e to the power minus 5t? This will be 1 upon s minus 5, that is 1 upon s plus 5. Okay. One more, what will be the Laplace transform of e to the power 2t? This will be 1 upon s minus 2. If you want, you can write s is greater than minus 5, and here s is greater than 2. Okay. To find why I am writing this is your task. Okay. If you, if you are not able to find why I am writing this here, you ask me. Okay. Now let us see one property of Laplace transform, and the name of that property is linearity property. Like derivative and integration follows linearity property, this operator, Laplace operator, also follows linearity property. Let us write the statement of that property here. Linearity property of Laplace transform so let us write the statement first. Let f1 f2 so on fn be real valued functions of t greater than 0, okay, and c1 c2 so on cn be arbitrary constants. Then Laplace transform of c1 f1t plus c2 f2t plus so on cn fnt equals to c1 f1s plus c2 f2s plus cn fns. I hope you are getting this. In short, or in the simpler way, this can also be written as in sigma form, that is sigma Laplace transform of sigma ci fit I varying from 1 to n equals sigma ci fi s I varying from 1 to n, where fis equals to Laplace transform of fit, okay, I equals to 1 to n, okay. So let us see the proof of this. You do remember this linearity property. So proof, we start from the definition of Laplace transform, or first we write f of t. Let f of t equals to c1 f1t plus c2 f2t plus so on cn fnt, okay, where ci's and fi's are constant and real functions of t respectively, okay. Now by definition of Laplace transform, Laplace transform, what we have, Laplace transform of f of t equals to integration from 0 to infinity e to the power minus st f of t dt. But what is f of t here? E to the power minus st, f of t is nothing but c1 f1t plus so on cn fnt dt. This equals to integration 0 to infinity c1, open this bracket and multiply each term of this bracket by e to the power minus st. Okay. So this is c1 e to the power minus st f1t plus second will be c2 e to the power minus st f2t, so on cn e to the power minus st sorry fn t dt. And as we know, integral is linear, or integ integration we can use the linearity property of integration, integral sign, or particularly we can say integral operator follows linearity property. So by using that you will get c1 integration from 0 to infinity e to the power minus st f1t dt plus so on integration cn into integration of e to the power minus st fnt dt. So again, by using definition of Laplace transform, what will we get? C1, this is the definition of Laplace transform of f1t. So we write Laplace transform of f1t plus so on cn, this is the definition of Laplace transform of fnt. You can give the reason here by definition. Okay. And Laplace transform of f1t is denoted by capital F1 as plus so on Cn capital Fn s. Okay. So what is the left hand side following up? This is Laplace transform of f of t. Okay. So what was f of t? It was the sum of c sum of product of constant cr and fit, I varying from 1 to n. And what this side has become? This is the sum of constant c i's and fi's. Okay, I varies from 1 to n. I hope you understood this. So Laplace transform of sum of product of constants and the function fi equals to sum of product of constants and Laplace transform of fi, that is capital Fis. Okay, so this shows the operator L, that is the operator Laplace transform follows linearity property. Okay, you take a note of this equation. Okay, so let us see few examples based on this linearity property. But before that, let us see Laplace transform of trigonometric function. Okay. So number 3, f of t equals to sine 80. Okay. Let us give the function f1t and set f2t as cos 80. We are going to find the Laplace transform of this function and this function, that is sin 80 and cos 80. So first we find the Laplace transform of sin 80. Okay, so I hope you remember the formulas for sin 80. So we know that, what formula I am speaking about? Sin 80 equals to e to the power I 80 minus e to the power minus I 80 upon 2i. And what is the formula for cos 80? This is e to the power I 80 minus, plus e to the power minus I 80 upon 2. We will find the Laplace transform of these functions by using these formulas. Okay, so now Laplace transform of sin 80 is nothing but the Laplace transform of e to the power I 80 minus e to the power minus I 80 upon 2. So as 1 upon 2 is constant, and we just have seen that this L operator follows linearity property, that can be taken out. Okay, and what remains here? Laplace transform of e to the power I 80 minus Laplace transform of e to the power minus I 80. Okay, so as we have already seen the formula for Laplace transform of exponential function, and what was that? Laplace transform of e to the power 80 was 1 upon s minus a when s is greater than a. Okay, we will use this formula here. So Laplace transform of sin 80 equals to 1 by 2 Laplace transform of e to the power I 80 will be, see this formula, 1 upon s minus, what we have in place of a, the coefficient of t, ia. So this is 1 upon s minus ia minus, what will it be, the Laplace transform of e to the power minus I 80, this will be 1 upon s minus minus IA. So you can solve this easily. So Laplace transform of sin AT equals to 1 by 2. Take LCM of these two. This is nothing but s plus IA. So this will be s minus IA into s plus IA. This will be s square plus a square. Okay. And what will be here? This will be s plus IA minus s plus IA. You can get this easily by solving 1 upon 2 into this s and this s will get cancelled. IA plus IA 2IA upon s square plus a square. So this 2 and this 2 gets cancelled, and the final answer we get as Laplace transform of sin AT equals to wait, I did do one mistake here. While writing the formula for sin AT, I have forgot to write I here. Okay, so you follow this I here, I, I, I. So not only 2, this I will also get cancelled. So what remains here? Laplace transform of sin AT is a upon s square plus a square. Okay, and here again I have a task for you. Find out why am I writing s is greater than a. Sorry, s is greater than 0. Okay, so do find. So this is the formula for Laplace transform of sin AT. Here a is any constant. Okay, so what was the second function? Cos AT. Next, Laplace transform of cos AT equals to Laplace transform of e to the power I AT minus plus e to the power minus I AT upon 2. Here there is no I. So if you want to do this as your practice, you can pause this video and start calculating or finding the Laplace transform of cos AT. Otherwise, you can continue the video. So you can bring 1 by 2 common, not common, out of this Laplace transform. As we know, this operator follows the linearity property. Okay, so what remains inside? Laplace transform of e to the power IAT plus Laplace transform of e to the power minus IAT. What will be the Laplace transform of e to the power IAT? It is 1 upon s minus IA plus 1 upon s plus IA. So again After similar calculation, we will get the denominator s square plus e square. And what will be in the numerator? 2s. Okay. So here 2 will get cancelled, and the final transformation of cos 80 is s upon s square plus a square. Okay, s is greater than 0. You do remember this formula. Okay, if you are not able to find this why am I writing s is greater than 0, you can ask, or I will tell you this in the next video. Okay, so as we have uh, found the Laplace transformations of sin 80 and cos 80, we can also find the Laplace transform of hyperbolic functions. So number 4 can give, if f1t is taken as sin hyperbolic 80 and f2t as cos hyperbolic 80. If you know the formula, you can pause the video and start finding the required, not required, the transformation for sin hyperbolic and cos hyperbolic. Otherwise, continue the video. So we know that formula for sin hyperbolic 80 as e to the power 80 minus e to the power minus 80 upon 2. There is no I here. And cos hyperbolic 80 as e to the power 80 plus e to the power minus 80 upon 2. So we first find the Laplace transformation of sin 80. So Laplace transform of sin hyperbolic 80 equals to Laplace transform of e to the power 80 minus e to the power minus 80 upon 2. By using linearity property of Laplace transform, we can bring 1 upon 2 out of this box. So Laplace transform of e to the power 80 minus Laplace transform of e to the power minus 80. This equals to 1 by 2 Laplace transform of e to the power 80 is 1 upon s minus a minus, this will be 1 upon s plus a. And after evaluating this bracket, you will get in the denominator s square plus, minus, let me clear this, s square minus a square, and in the numerator what will you get? 2a. Okay, so these two and these two will get cancelled, and what remains? A upon x square minus a square. But do remember, denominator, this transformation must be well defined. So denominator should not be 0. So you always keep s is greater than modulus of a with this transformation. Okay. So this is the Laplace transformation of sine hyperbolic function. Okay. This is your homework. Find Laplace transform of cos hyperbolic function. Okay. The answer I am writing here. This is s upon s square minus a square with s is greater than modulus of a. Okay. You do find. If these examples are clear to you, we can take one example which will cover all of these functions, okay, and the linearity property also. Example, find a Laplace transformation of 3t square minus 2e to the power t plus sine hyperbolic 3t plus 5 cos 4t. If you want to try, you can pause the video or continue. So we can do that directly by using the linearity property. So by linearity property of Laplace transform, we have Laplace transform of 3t square minus 2e to the power t plus sine hyperbolic 3t plus 5 cos 4t equals to, because of lack of space here, I will write that just below this. Okay. So what will we get by using linearity property? This is 3 Laplace transform of t square minus 2 Laplace transform of e to the power t plus Laplace transform of sine hyperbolic 3t plus 5 Laplace transform of cos 4t. What will be next step? 3 into what is the Laplace transform of t square? T to the power 2. We have already seen. Let me show you again. Laplace transform of t to the power n. See, Laplace transform of t to the power n is n factorial upon s to the power n plus 1. Okay, so this we are going to use So whatever transformations we have obtained till now, all we are going to use here in this example. Okay, so Laplace transform of t square will be, this is 2 factorial upon s to the power n plus 1, that is 2 plus 1 minus 2 into what will be the Laplace transform of e to the power t? It is 1 upon s minus a. A means coefficient of t. Here coefficient of t is 1. So this is s minus 1 plus, this is sine hyperbolic function. So its Laplace transform is a upon s square minus a square. Okay. So this is 3 upon s square minus 3 square, that is 9. So plus 5 into Laplace transform of cos 4t is s upon h square plus 4 square. 4 square means 16. Okay. So 2 factorial is 2. 2 3s are 6 upon s cube minus 2 upon s minus 1 plus 3 upon s square minus 9 plus 5s upon s square plus 16. Okay, and do remember here s is always greater than 3. S is greater than 3 because of this. Okay, so this all these were the few examples, one theorem of this unit. The remaining examples and theorems we will cover in the next video. Thank you.